All right, thank you so much for having me here. It's such a nice conference. I excuse me. It's a great lineup, so I'm really looking forward to all the other talks. I want to start by sort of sharing some of my experiences based on some of the data that we have collected over the years. I really don't have a final, you know, big message, but what I wanted to say is that multiphase is really our friend, and that's what we really want. It's not really a problem, which sometimes come up as a problem because it's hard to interpret. So what I want to say is that we have always been thinking about galaxy evolution in terms of how things are going into the galaxy, how things are going out. And in that picture, multiphase is really necessary to really understand things going out, of course, which we see as outflows. We see as cold outflows, hot outflows, wind fluids, extremely hot, even molecular gas, very, very cold in outflows. So that is something we really know. But also for inflow, if we have just a virialized CGM, we can all go home and be happy that we have solved it, but really that's a very big problem for getting gas into the galaxy. So multiphase is essentially not the problem, but actually the solution to our problems. Now, the task at hand is to understand how we can decode what we observe or what we have in our simulations to understand these different processes in terms of galaxy evolution. So as I said, I'm going to share some of my data. There's a wide range of data, some of it collected by us, some by others. And I'm just picking a few here, but this is not to say that these are just one. So here is a starburst galaxy, and so that's a starburst galaxy, kind of 10 power of 5 solar masses in stars. Very similar to Milky Way. This is about 100 kpc away a quasar. And what we find is, again, multiphase gas, but in this case, the gas that we see is differentiated in velocity. So now we can actually see that there are these different phases. So you see the cold phase, which is Lyman alpha, beta, in this case, silicon 2, 3. And then, of course, we also had a little bit of silicon 4. It's not plotted here, but oxygen 6 really shows up a little bit for the cooler component, which is, as we understand, is the outer shell of these cold clouds, photoionized gas. But then you do see this stuff. But we are lucky that we have this orientation in such that these velocities are deprojected. It could very well be that all of it is in the same velocity space just because of our projection. And we might be dealing with cases where things are not split out, but we have to sort of pull all of these together. And at that point, we are limited sometimes by our observations, but also sometimes by modeling. I just wanted to share something new also. Again, in the same spirit, here is another galaxy. This is the COS Magic survey. It's a new survey that's almost done taking data with HSD COS. The idea is to look for the CGM in these 3 ions, oxygen 6, carbon 4, and nitrogen 5, the hot phase, all the 3 ions together, so that we can understand what's going on with the physics of the winds. But that was the goal. But what we found in this case, this is absolutely new data, so we have just fitted it. But we found a lot of molecular gas right at the position of the quasar from the galaxy. This is a star-forming galaxy. Of course, we have everything else, including oxygen 6 as well. So we're trying to model this. But clearly, this is a case of multiphase CGM. Now, we don't think that it is an IGM of a smaller galaxy here. I mean, it's unlikely, I suppose. We don't see any H alpha coming out of that at the position of the quasar. And also, we find that the phase of the gas is kind of interesting. People have, I'm so sorry about the quality of the plot. Not sure why it landed up. But the point is, this is the fraction of molecular hydrogen. This is the total atomic plus molecular. And people have made these plots. Some of them are already in the room. But this system lands up in here. And the point I want to make is that our H1 measurement is pretty consistent. It's from the sight line. It's not using 21 centimeter or something. So we are not looking at different clouds. But in this case, you're finding 21 centimeter, H1 cloud of 10 power of 18 with molecular hydrogen, which is kind of not what you think if you're thinking in terms of ISM. So at this point, we haven't done really an analysis to actually tell you, but it seems like there might be some kind of interaction or some kind of flotsam that's coming out of the galaxy and the CGM. Not sure how I'm doing on time. But the other things we can do, now that we have gone to the multiphase systems, we have multiple ions, and the ratio of these ions, if you have them for the same system, it's really powerful tool. And I wanted to show you, again, from the CosMagic data set, we have the whole data set was designed to have these ions, carbon 4 and oxygen 6 and nitrogen 5. So you can actually plot these in this diagram. This has been done from the Milky Way, HVCs, Andy is here and others who have done this. But as Andy would say, this is our VPT diagram equivalent. But different ionizing processes land up at different places with very little overlap. So essentially, this really gives us a sense of what the process might be going on that's producing this kind of different phases, and it could be actually very transient. So that's for CosMagic. We have also done the same stuff for a blind survey for intergalactic medium sources. We just looked at the Danford catalog and picked all the samples, all the systems where we have data for all these 3 lines, and then plotted it. And it turns out in both the cases, conductive interfaces between clouds is really, a lot of points are landing over here. There is radiative cooling and shocks and turbulent mixing layers over here. So they are all the same. It's basically the same thing. But what we're finding is that a lot of points are landing in conductive interfaces, and that's very similar to what people have seen in the Milky Way halo. So there might be something there that's telling us what might be the interactions. Okay. All right, I'm going much slower, so maybe I have to pick and choose. So that was a lot of outflow. We can, as I said, Milky Way, people have seen it, the HVCs. We have also now started seeing HVCs, and other galaxies are just, there are a lot of data now on many NGC galaxies. So this is just one of the examples, but it's a really nice example where the quasar sits on the ISM. So you can see 21 centimeter maps and see the kinematics of the ISM. But then if you look at the absorption, what you find is that you find an HVC about 345 kilometers from the systemic. And this is very similar to what we see. It's metal rich, so it might be something like what we have in conventional stem of something that might have come out of it, stayed in the CGM, and come back out. But even in these models, what's most interesting is that things are multi-phase. And if we have enough data, and if we have better models, we can actually really see whether we're seeing something like this or not with the kind of data that we are getting, and in the future we will be getting. Anyways, so in the last few minutes, I want to highlight a few things that it's not essentially multi-phase related, but it's still interesting in the buildup of disk. So one of the things that we have found is people have plotted equivalent width and distance quite a bit, but this is a slightly different normalization. In this case, it's the H1 radius. And what we find is that this is a really strong trend that we see here. It's much less noisy than when you plot R virial in this case, or just the impact parameter. So this is impact parameter normalized by it. So let's just skip this. Also, for the same set, you can also see this trend in metal lines. All right. And you can measure cloud sizes and stuff like that. But I think at the end of what I wanted to mention is, moving forward, we have to sort of think about the next mission that's coming up, not immediately, but we have to sort of get our act together. And the habitable worlds, one of the really important, exciting things that's coming up as the driver for design of the instruments is the CGM science, both absorption as well as emission. So I would encourage you to think about these things. Time is actually short. We have to come up with these science cases by end of the year. So essentially, if you have a science case and you have specific requirements for the instruments, like resolution or coverage in the blue, please feel free to talk to me or come to our meetings in the Habitable Worlds Observatory. And yeah, I think I will leave you with this. But I think at the end, we need to continue gathering data. We need to continue modeling. And multiphase is the solution to our biggest problems. I'll stop here.
Question, Charlie?
So that system you detected H2 for, that's really interesting. I wonder if you saw any, I suspect it's probably high density, high metallicity, maybe dusty, likely dusty. I wonder if, have you detected sodium-1, for example, or calcium?
So we have SDSS spectra, and it's not good. So we are trying, it's not good signal to noise in terms of the resolution signal to noise. So there we don't see anything. But there could be a very narrow sodium component that might be hiding at the resolution of SDSS. So we are planning to get high resolution data. So that will be something really
and you
important.
mentioned, sorry.
Yeah.
You mentioned there's H alpha limit.
Yes, so from the quasar spectra at the position, from the quasar spectra at the position of, at the redshift of that, we do not see any H alpha emission. So we think that this must be something, you could hide a star forming galaxy, LMC or below, but not above.
Yes.
Thank you, Sanj, for the lovely talk. So back to your CGM EPT plot, which we need a better name for. But the nitrogen 5 is something I've been interested in for a while, and I noticed in your stack plot there was no nitrogen 5 detection for at least the one cost magic system you set. But then on the points on your plot with the nitrogen 506 on the x-axis weren't limits, right? So do you detect nitrogen 5? Or
So we only plotted the ones that were detected.
Okay, you only plotted the
Yeah.
Gotcha.
Yeah.
Okay.
Yeah, so when you have a limit, well, we should have, but it doesn't give it, it was on the other side, so it's basically any of the models are.
Sure, yeah. Limits.
Yeah,
Great.
so that's why we don't have. Yeah, but we don't have as many detections of nitrogen 5 as carbon 4 or oxygen.
It would
Oxygen
be
6
interesting to know how many non-detections versus detections in nitrogen 5.
Yes, I should have that information somewhere, but not with me. But I can, we can talk more.
Yeah, I'm excited.
More questions? Yeah.
May I please ask, there are so much ionized gas in this outflow procedure. How would the magnetic field play a role when interacting, when like the outflowing procedure, and how it interact with the CGM?
I don't know, to be honest. I have seen conflicting results of people saying, I guess it also depends on the strength and the direction of the magnetic field, but I have seen conflicting results where people have seen growth of cooler structures versus not so much. So it's actually on the theorist, because I really can't measure any magnetic field at this point. But I think some of the non-equilibrium processes that we are talking about at this stage and beyond, I think magnetic fields are really, might be the difference between some of the things matching our observations or not, the models. Yeah, so it's really important to now think about magnetic fields in the context of hydrodynamics.
Thank you.
I don't know, final time. Thank you, Sanch, again.